All right, hello everyone. Thanks to those of you who are here and to those of you who are tuning in online. Up next, we have Dr. Dirk Notz from the University of Hamburg speaking to us about sea ice as an indicator of climate change.
Yes, hello, thank you. It's great to be here. It's great to see you, and it's great to see all of you. No, not seeing you, all of you online, but knowing that you're somewhere out there. Even though the topic that I'm going to cover today isn't possibly the most positive one, because I'm talking about the disappearance, really, of Arctic sea ice. And maybe just in order to set the scene, I just would like to have you look at two pictures from the same region, from the same time of the year. This is from an old expedition in 1912, a German expedition that went to a bay in Spitsbergen called Sorge Bay. They had plans of crossing some glacier there and then sailing back. But that expedition back then ended as a catastrophe because their ship got entrapped by sea ice in September 1912 in this bay. And I was there, not on this expedition, even though I was asked whether I was there by a school kid, like 6, 7 years old. When I showed this photo, she asked whether I was there on this 1912 expedition, so I told her no, I wasn't. But I was in the Arctic on a similar sailing vessel a couple of years later, 2007, in the same bay, same region. And there was just no danger whatsoever for us to get entrapped by sea ice on our ship. And we really had to sail very far towards the North Pole, about 400 nautical miles towards the North Pole, before we hit the first sea ice floes on the open water. And so this was basically the ice edge that would then stretch to the North Pole. And we were really close to the North Pole. So from where we were here up to the North Pole, it would have been another 500 nautical miles to sail. And we probably were the sailing vessel that was able to go in open water closest to the North Pole ever. So the ice edge was really, really far north. And it was amazing for me to see how the landscape had changed between that expedition back then and our expedition in 2007. But of course, this is just one snapshot from one region, one fjord, 1 year. But this snapshot actually is found to be correct if we take a bit of a step back and look down at the Earth from satellite, because these satellite images really confirm this notion of disappearing sea ice. So what is shown here is a satellite image from the 13th of September 1988. End of September, mid-September is usually the time of the year when the sea ice coverage on the Arctic Ocean reaches its minimum extent because it has been melting throughout summer. But you saw 30 years ago, still the Arctic Ocean was basically covered in sea ice at the end of summer. So this was 13th of September 1988, and this is 13th of September this year. 30 years later, the area of Arctic sea ice has roughly halved. And the ice floes that are left here are only about half as thick as compared to what they used to be. So in terms of sea ice volume, this is about a quarter of what we had 30 years ago. So over the past 30 years, we've melted, we've lost about 3/4 of Arctic summer sea ice. 1/4 is left. And what we try to understand in our research group at the University of Hamburg, in our CS research group, is what will happen to this last quarter. Will we be able to save it somehow? Or will the Arctic Ocean look like this in the future? An ocean just like any other ocean in summer without any ice on it, where you can just board any boat and go to the North Pole and look at the water at the North Pole. And that's a bit also the topic of today's presentation as to what the future of Arctic sea ice will look like. And we also see later on why this disappearance of Arctic sea ice is something that is of direct relevance to all of us. But before we get into the more scientific aspects of why this disappearance of Arctic sea ice is so important, I would like to just briefly talk about one item of why this disappearance of sea ice matters that is very dear to my heart, because I do give a lot of presentations at schools to kids, for example, and I'm always amazed by how ice is fascinating for them. So when I show them these kind of pictures, how often they would look with really big eyes and look at these landscapes and how they are fascinated by ice, by cold. And I think as we're now approaching Christmas, for example, this notion of Father Christmas and his icy landscapes, this notion of actually us making these landscapes disappear, making these icy landscapes disappear from our common heritage of what this planet looks like, that there are regions that do look like this, I think it does something to how we see the world, and it takes away a lot of dreams from our children. It takes away the way they have this sort of adventurous view of what the Arctic is about. And it does change something in all of us, I think, if we lose the ice on this planet. It will not be the same vision of our planet that we used to have throughout our civilization. So we're actually destroying some common cultural heritage that somehow deep within us rings a bell when we see photos of ice, of this incredibly beautiful landscape. But ice is not just a common cultural heritage, but it is also, of course, very, very important for us climate scientists. This is photos not from sea ice, but from the ice sheets we have in Greenland. And I would like to just give you a brief overview of climate history seen through the eyes of somebody who's interested in ice. And much of what we know about the past evolution of our climate system is actually frozen in this ice we have in Greenland, we have in the Antarctic. So these are not the ice floes floating on the ocean, but this is ice lying on land. And this ice lying on land is nothing but really, really old snow. So you can imagine in Greenland and Antarctic it just snows in winter. The snow doesn't melt in summer, so the next winter you have new snow on top of that. And so after a couple of 100,000 years, you have a lot of snow lying there, and this snow is then being compacted and transformed into ice. And this is how these ice sheets form in Greenland and in the Antarctic. And if we now stand on top of it and you drill downwards, you make a journey through time, through snow that fell last year, 100 years ago, 1,000 years ago, 10,000 years ago, 100,000 years ago, 500,000 years ago. And we can analyze this kind of snow. We can analyze what the air looked like back then. We can analyze what the temperature was. We learned a lot about the past evolution of our climate. And through all sorts of other methods and additional methods, we do know that the amount of ice we've had on our planet has been changing enormously throughout the history of our planet. So if we go, for example, 800 million years into the past, this is roughly how Earth would have looked like back then. It was basically all covered by sea ice, according to everything we know today. We call it the snowball Earth, a very stable, very cold planet. All the sunlight that would hit the surface, most of that would just be reflected back to space, keeping the planet really, really cold for millions and millions of years. So that was 800 million years ago, much more ice than today. Then about 100 million years ago, when the dinosaurs were walking through these conference halls, it was much warmer than it is today, about 14 degrees warmer on the annual average. There wasn't much ice on this planet. There was nothing in the Antarctic, nothing in Greenland. The very highest mountaintops, they might have been covered by some ice, but it was certainly far, far less ice than we do have today. And from this period onwards, from this period 100 million years ago, when it was 14 degrees warmer than it is today, we've slowly had been seeing a cooling planet. This is shown here. So this is what we just had here, this green region here. And from then onwards, it was just getting colder and colder slowly over millions and millions of years, until we got cold enough to get into what we call the Ice Age cycle, that is shown here from these ice core measurements in the Antarctic. And the thing that I would like you to focus on is this top graph here, just showing how every 100,000 years, over the past hundreds of thousands of years, we move into an ice age, stay in there, then move out again, move back in again. And so climate on this planet and the amount of ice we have had on our planet has always been changing. That is one message. But if we look into the past 50,000 years, again, if we start from the left here, 50,000 years ago, we do see all these climate fluctuations, all these fluctuations in how much sea ice we have included. But then 10,000 years ago, we suddenly entered a period of an incredibly stable climate. Incredibly stable in the sense that the temperature wasn't fluctuating very much. And everything we have in terms of our civilization development basically happened over those past 10,000 years. So we were still in a Stone Age at the beginning of this period. And then throughout this period of an incredibly stable climate, we moved to the civilization we have today. And I am convinced that this was only possible because the climate has been incredibly stable. And everything we have in terms of our civilization today, all the infrastructure, is perfectly adjusted to this climate state. Everything we have in terms of the agriculture, the kind of location of our cities, is perfectly adjusted to the amount of ice we have on this planet, to the weather patterns we have. And so what we're doing now is to basically make a very interesting, but I think really stupid sociological experiment, namely, what will happen to a civilization that hasn't seen any climate change throughout its entire development, or very, very small, very little climate change, if we suddenly give this civilization a completely new climate state? How will it react? And just to put things into perspective, on the next slide, you will see those past 10,000 years. You will see again the kind of climate change we've experienced so far in relation to what we expect for the future. And so this blue line here, that's the amount of climate change that our civilization has been through, basically nothing. Then this black line here, that's what we've achieved already in terms of global warming. That's where we are today. The green line, that's the line that's compatible with the text of the Paris Agreement. So it's about a 1.5 to 2 degree global warming world. And the red line, that's a global warming scenario that's compatible with the kind of actions that we've been taking so far. Very little reductions in CO2, basically CO2 emissions rising every year. And you see that by the year 2500, in this scenario, we do have a world that is more than 6, 7, 8 degrees warmer than what it used to be just about 150 years ago. And this 8-degree warming, just to put things into perspective, if we go back to this picture getting out of the dinosaur age, we last had these kind of temperatures about 40, 50 million years ago. And so it took the Earth 40, 50 million years to get out of that warm temperature period. And we humans are in principle capable of putting the timeline back by 40 million years over a period of just 500 years. And so the amazing thing about the temperature change that is going on now is, first of all, not amazing, but the threatening thing, first of all, that our civilization has not experienced any such climate change. And second of all, how incredibly fast these things are happening. And we do see the consequences of these ongoing climate change in everything that is frozen on our planet. For example, the Arctic sea, as we've seen that before, is melting really, really rapidly. And by doing so, what is happening in the Arctic is that the Arctic is losing one of its most important cooling mechanisms. Because today, where we still have sea ice floating on the Arctic Ocean, this sea ice acts like a big sunlight mirror. So most of the sunlight that hits the surface is just being reflected back to space, keeping the Arctic cold. But this sunlight mirror is just getting smaller and smaller and smaller. And so this cooling mechanism of the Arctic is getting weaker and weaker and weaker, which is one of the main reasons for why the Arctic is by far the fastest heating part of our planet. And so to me, this disappearance of Arctic sea ice in the Arctic, in addition to everything that it does to the climate system, to me really is one of the most important warning signs that the climate system as a whole is sending out to us humans, saying that there is massive change going on in the climate system of our planet, and we just see it first in the Arctic in this incredibly fast loss of Arctic sea ice. And just to put things into perspective of how fast the Arctic would be warming, this is a model simulations from various models, how the Arctic would look like in a world that is just 1.5 degrees warmer than it is today. And you see the scale on the y-axis that goes from 0 to 9 degrees warmer than it used to be, from January till December in the annual mean. And so in a world that is 1.5 degrees warmer on average, for example, in October or November, the Arctic on average would be 6 degrees warmer than it is today. In the annual mean, the Arctic would be 4 degrees warmer than it is today. In contrast, in a 2-degree global warming world, in November, the Arctic might be up to 8 to 9 degrees warmer than it is today. In the annual mean, about 5 degrees warmer. And so when we talk about a 1.5 or 2 degree global warming target, in the Arctic, there won't be anything like a 1.5 or 2 degree warming. It will be much more like a 3, 4, 5, 6, up to 9 degree global warming, changing the Arctic as we know it today to something that is unlike everything we've ever seen. And along with this really, really rapid warming we have in the Arctic, we do, for example, affect the melting of the Greenland ice sheet. So the Greenland ice sheet, as we've seen before, is a mountain of 3 kilometers of ice sitting on land. It's growing by snow falling onto it. And the problem that we have now is that this Greenland ice sheet, there is a tipping point in its melting process that might make it disappear at some point. And the reason for why this is, if we make the climate warmer, the surface of the ice sheet is getting lower and lower because we are melting the surface. And by getting to lower and lower levels, the surface of the Greenland ice sheet is getting into warmer and warmer atmospheric layers. Everybody who's ever climbed a mountain knows that if you climb down from the mountain, it gets warmer and warmer. And so basically, we make the surface of the Greenland ice sheet climb down the mountain into warmer regions. And eventually, it'll be in an atmospheric layer that is so warm that the melting of the ice sheet will just continue and accelerate. It'll get even lower, get into even warmer atmospheric layers, and so on and so forth. And so at some point between 1.5 and 2 degree global warming, amplified by these sea ice-related processes, for example, we will cross a point where we cannot stop the melting of the Greenland ice sheet anymore, giving rise to long-term sea level rise of 6-7 meters. One other aspect that is important when we look at this really rapid, strong warming of the Arctic relates to permafrost. So permafrost is this layer of frozen ground we have in the Arctic, covering basically all the land masses around the North Pole. And in this permafrost, there's a lot of organic matter stored. And as we warm the climate system, this permafrost layer that is always frozen will start thawing. And as it thaws, this organic matter will be decomposed by bacteria, by all sorts of activities, microbiological activities. And then in this decomposition, methane will be released. And this methane is a very, very strong greenhouse gas, much stronger than CO2. And a lot of that will just come out of the permafrost in this Arctic that is so much warmer than everything we know today. I should say, however, that some of the pictures that are drawn in the media of like basically this permafrost releasing twice as much carbon as we have in the atmosphere today, those are exaggerated because this process is pretty slow. But still, by the end of the century, in a 1.5 or 2 degree global warming world, the permafrost of the Arctic might be emitting as much carbon as any other big major country emitter, like Canada or the US or whatever. It's hundreds of millions of tons of carbon that will come out of these permafrost in this very fast warming Arctic. And this methane, and this is just the final slide to put things a bit into perspective as to what we are doing, as any other, or will add to the greenhouse gases we have in the atmosphere. And some of these greenhouse gases, some of these CO2 in particular, doesn't stay in the atmosphere, but it is being absorbed by the ocean. And so of all the CO2 that we humans are emitting, about 1/4 actually ends up in the ocean. And as this CO2 goes into the oceans become more acidic. And this is just, again, to put things into some temporal perspective. This is 22 million years or 25 million years of data that we have collected from the sea floor. And it shows on this axis here how acidic the ocean is. And what you see is that over the past 22 million years, the acidity of the ocean hasn't changed very much. It has been incredibly stable again. But what we see here is the kind of change that we could bring to the acidity of the ocean over a time span of just 100 years. It's beyond anything the ocean has ever experienced over the past 22, 23 million years. Just again, putting into perspective the rapidity and the uniqueness of the kind of changes that we do impose on the climate system of our planet. Now, having talked about how the amount of ice we had on our planet has always been fluctuating from like much more ice than we have today 800 million years ago to just no ice 100 million years ago, of course the question then arises, how can we be so sure that what is happening today is really caused by us humans? And there are hundreds of lines of evidence for that. Just basic physical understanding tells us that if we put more greenhouse gas into the atmosphere, it must get warmer. It's basic physics. There's nothing to be argued about. But there's all sorts of other lines of evidence too. And one of the main things I would always have loved to do is an experiment where we just rebuild the solar system with the sun and the earth and just leave out humans and see how that climate would have evolved. However, we never really got funding to do such an interesting experience. And so what we did was to do the second best. We rebuilt the climate system of our planet in a computer. And in this virtual computer world, we could then just leave out the humans. And if we do that and we ask the computer on this planet that we've just created within you, how would the temperature have evolved over the past 150 years if humans wouldn't have existed? And the computer then spits out this blue line and says, oh, it's probably quite stable, nothing really much going on. And that doesn't fit very well to the kind of temperature evolution that we have seen, that we have observed over the past 100 years or so. And then we can take this same virtual world in our computer, and we can tell the computer, well, there are humans, we tricked you, and these humans have emitted a lot of CO2. So tell us, what should the temperature have evolved like then? And what the computer then spits out is this pink region, and it fits perfectly to what we observe. And this is just one additional lines of all these evidences we do have for why we are so certain that the ongoing ice loss really is caused by us humans. But of course, everybody dealing with computers might be skeptical and know, well, you never know what computers do. So I just brought you one additional line of evidence where there's no modeling in there whatsoever. It's just based on plain measurements, very, very simple measurements, because we do have very reliable measurements of how much CO2 we humans have emitted so far. or we have data on that, and we do have very good measurements of how much sea ice there was in the Arctic over the past 60, 70 years. And if we just plot these two pieces of information against each other, if we plot on this axis here how much sea ice we have in the Arctic, and on this axis here how much CO2 we humans have emitted since 1850, we see this incredibly clear, very linear correlation. And this kind of very linear correlation we see also in every single climate model we have. It's a very, very robust feature of the system that the sea ice reacts directly to the amount of CO2 we have in the atmosphere. And this picture then also just gives us the answer as to what the future of Arctic sea ice will look like. There is no magic year as to when it disappears, but there is a magic number of how much CO2 we can still emit until Arctic sea ice is gone. It's a very, very simple relationship. We know from model simulations that we can just extrapolate it into the future. And the magic number ends up to be at around 800 gigatons of CO2. And at today's carbon emissions, that would be in about 20 years' time, plus minus 10 years roughly, because of fluctuations, natural fluctuations in the climate system. So for today's carbon emissions, the Arctic would be ice-free between 10 and 30 years from now. And so the time window to save Arctic summer sea ice is closing incredibly fast. The second thing we can do with this kind of data, we can just calculate the slope to calculate how much sea ice is actually disappearing for every ton of CO2 that we are emitting. And if we do that, we come up with a very simple number, namely that for each ton of CO2 that a human emits anywhere on this planet, the amount of Arctic sea ice in summer shrinks by about 3 square meters. And so I'm from Germany, and we in Germany, we emit every year about 10 tons of CO2 per person. And so each of us in Germany, on average, every year melts an area of Arctic sea ice that is about 30 square meters, so roughly the size of this room here. That's the amount of ice floes that each German melts every single year, according to this relationship. We can also, I've just put this into the sort of context of how much CO2 we can still emit. We can, of course, also just put this into context of the temperature when the Arctic sea ice disappears, because we also know at which CO2 emissions we reach which temperature limit. And what we see from that is that in a world that is 1.5 degrees warmer than it is today, we will still have Arctic sea ice all year round, whereas in a world that is about 2 degrees warmer than it is today, the Arctic Ocean in most years will be ice-free in summer. So yet again, from a cryospheric perspective, the difference between 1.5 and 2 degrees is huge. As we've seen before, this difference can mean whether we can still stop the melting of Greenland or whether we can't. Here we see that this difference means whether we do have sea ice all year round or whether we don't. Now this linear relationship holds for all years, so we can actually exploit it, or we can have a look at how the Arctic Ocean looks like for future CO2 emissions along this line down here. And I often, when I look at this, and people often tell me, well, this is just so frustrating, I think it's actually a great thing that we know that all the change that we are seeing in the climate system is caused by us humans. I think I would be much more worried if I knew that all these changes are just coming from somewhere else, from the sun or something else, because then we couldn't control it. But because it comes from us humans, it really is in our hands and our control how the Arctic Ocean will look like in the future. We can still change the future by our actions, by our decisions, by our negotiations here in Madrid. We can still decide whether we will eventually reach, say, 1,000 gigatons of CO2 emissions in 25 years or so, having an Arctic Ocean that is ice-free throughout August and September, or whether we don't, whether we just emit another 400, 500 gigatons of CO2. That is our decision as humanity. It's our decision how the future will look like. And so finally, just to show this, that we do have the choice, and what the choice actually is, I've just brought one final animation of just two Earths. The one on the left is one where we as humanity decide we would like to put action into the words of the Paris Agreement. We would like to make the Paris Agreement become reality and not just be existing on paper. So this is a world where we do cut emissions so fast that we can achieve a 1.5 to 2 degree global warming target. Whereas the one on the right is a world where we just continue what we're doing just now, basically emitting CO2 basically the way we've been doing it forever, or for the past decades, without really slowing it down. And these two planets will start spinning soon, and you will see the year going up from 1986. And the colors on these two planets, they indicate how much warming we have or expect for the future relative to what we have today. And so you see, of course, for the past, it's very hard to change the past. So for the past, these two planets will look very similar. And also for the immediate future, until 2025, 2030, it's hard to see any difference between these two. But then from 2030 onwards, you really see the impacts of our decisions here in Madrid, for example. You do see how it does make a difference what is being decided here. And this really, from a scientific perspective, is the choice that we have as humans, whether we will live in a future that looks like that or a future that looks like this. And this is the main thing that science really can bring to this conference, that we do have the choice, and it is really the choice that we as human society have to make at some point, whether we want the world to look like this in the future or whether we want it to look like this in the future. And so to just quickly summarize, we do know that Arctic sea ice is melting very, very rapidly. And we do also know that the Arctic will lose its sea ice cover for an additional about 800 plus minus 300 gigatons of CO2 emissions, which is about 20 times today's annual emissions. So in 20 plus minus 10 years, so in 10 to 30 years for today's emissions, the Arctic will have lost its summer sea ice cover. So there is about a 5% chance of seeing an ice-free Arctic Ocean in just 10 years. And so as I said, the time window to make sure that we do have sea ice all year round is closing very, very rapidly. Because of this sea ice loss, the Arctic is warming very much faster than the rest of the planet. And this strong warming, for example, leads to additional ice sheet melt, sea level rise, and permafrost thaw, with all the implications for the rest of the planet of rising sea levels, rising temperatures because of additional greenhouse gases from permafrost, and all the consequences it brings to low-lying islands, low countries, ocean acidification, etc., etc. We've also seen from this very clear linear relationship that there is no tipping point for Arctic sea ice. Unlike for the Greenland ice sheet, there is a tipping point at some point between 1.5 and 2 degree global warming. We cannot stop the melting of this Greenland ice sheet anymore. For Arctic sea ice, it's much simpler. The Arctic sea ice will just look at how much CO2 are we humans emitting and will behave accordingly. So for each additional ton of CO2 that we are emitting, the ice cover will shrink. It's a very, very simple relationship, which then also implies the very, very simple physics-based claim that in order to stop sea ice loss, the world must become carbon neutral. It's as simple as that. As long as we keep adding CO2 to the atmosphere, Arctic sea ice will continue to melt further and further and further. And that's basically all I wanted to share with you today. If you would like to have the slides, if you want to have any additional questions beyond what you can ask now and today and here, please send me an email. I'm very happy to share all of this. But for now, I'm just extremely grateful that you're all here, and I'm very grateful for your attention. I'm happy to take any questions. Thank you very much.
Are there any questions?
Yeah, I just thought I'd mention briefly, there are a lot of initiatives going on trying to protect the Arctic in this changing world. One that is on the table here is a statement by the Clean Arctic Alliance that is working to make a heavy fuel oil-free Arctic that is being taken on actually by a growing number of countries. There is talk perhaps of marine protected areas. But I wanted to emphasize in a way Dirk's last point that really the only way to protect the Arctic is by decreasing emissions. Those are more kind of adaptation measures to adapt and help to preserve a changing Arctic, but to prevent those changes, we need to follow these 1.5 degree pathways. So.
Thank you very much for giving us this shocking wake-up call, these alarming findings. These are the physical and chemical processes, but what does it mean for the life in the Arctic region, for the ecosystems and for the people, for the culture there?
Yeah.
So a couple of years, a couple of decades, then what does it mean?
Yeah, that would be a presentation really in itself. If we just start with your second point, the indigenous population of the Arctic, they really do know and feel all of this already today. So for example, I've been working in Greenland a couple of years ago and talking to the people there. They just say, I don't understand. They don't understand how anybody can still sort of just talk about climate change, because for them it really is part of their daily life. It really is reality. So for example, they told me that they don't need their dogs anymore. They just shoot all their dogs because they can't use them to travel over the ice anymore. They would just be fishing all winter long, and but in doing that, they would often find fish or catch fish now for which they don't have a word in their languages, because the water has become so warm that they do get species they've never seen before. They used to just have the fish drying in the air and was all fine, but they can't do that anymore because of insects coming now and putting their eggs into the fish, so they have to build sort of refrigerators and everything. They are just trying to adapt to all these massive changes that are going on, and they cannot keep up their traditional lifestyle. And that, of course, brings with it a lot of sort of feeling of being lost. If they have nothing that they can relate to anymore, to some degree. All the traditions, all the culture they have, a lot of that is just perfectly adjusted to having ice, and all this is just disappearing, and they can't hold it. So it's basically running through their hands, causing a lot of difficulties in maintaining a healthy lifestyle in the Arctic. The same, of course, holds for the ecosystem of the Arctic Ocean. The ecosystem of the Arctic Ocean is perfectly adapted to the existence of ice. I showed this photo of polar bears. We do expect polar bears to be able to survive even if the ice completely disappears in summer. They would just go closer to civilization, go through rubbish bins, try to find something to eat there. But there is an entire ecosystem that will just disappear, that needs sea ice all year round, like seals and a lot of small sort of krill-like stuff, needs algae hanging down from the ice. And so that ecosystem will disappear. And it will make space for ecosystem from the south to slowly move northwards and take over, basically. But the ecosystem that is at the north already cannot move any further north, so it will just disappear.
Other questions? Thank you.
Well, thank you. Thank you.
Thanks for joining us. Up next at 4 p.m., we are going to have Dr. Hugelius calling in from University of Stockholm to give a really excellent presentation on permafrost. And then at 5 p.m., we'll be talking about ice sheets and sea level rise. Thanks. Joined us in the Cryosphere Pavilion today. We have Gustav Hugelius on the line from Stockholm to talk with us about permafrost. All right, and Gustav, I'll just mute myself, and then you are good to go now.
Thank you, Hannah. Thanks for introducing me, and thanks to all of you or to those of you that came to listen. So I'm going to give you an overview talk about permafrost, climate, and carbon. So trying to summarize the key messages from the recent policy report on Cryosphere and the 1.5 degree warming scenarios. So I'd also like to acknowledge my co-authors on Sue Natali from Woods Hole Research Center and Sarah Chadburn from the University of Exeter contributed to putting this presentation together and also a lot to the report. So I'll start with a slide summarizing background. What is permafrost? So permafrost is basically ground that remains frozen all year round. And it covers a very large area in the Northern Hemisphere. Roughly 14 million square kilometers is affected by permafrost in the Northern Hemisphere, and that's the whole area of the European Union times 3. So it's a really big area. And importantly, most permafrost is several thousand years old. So the permafrost doesn't only consist of soil, but it also consists of organic material and actually a lot of ice that is in the ground, sometimes not visible from the surface, but below ground it can be very ice rich. So the photographs you see here are of 2 different types of permafrost deposits. And on the right you do see a head wall of a big thaw feature that's developing in the high Canadian Arctic, and there you can see that the ground there is basically made up of more ice than soil. So most of the below ground material is ice, and when that melts, the whole ground slumps together. On the left hand photograph you see a permafrost peatland, so an area with purely organic soil that is affected by permafrost. So in that case the permafrost is actually only composed of frozen plant remains. There's almost no mineral soil there, but mainly just plant remains. So this high stock of these plant remains have accumulated over a very long time, which means that there's a lot of carbon stored in permafrost, which can then respond to the climate change. So we're presently at about 1 degree global warming above the pre-industrial temperature. And this means that we've already warmed the Arctic quite a lot, and there has been a loss of permafrost already. So with the warming that we have now, models predict a loss of permafrost that is since the pre-industrial that you see in this map here, which is centered on the North Pole. And you see the permafrost region in Siberia on the upper right and in North America on the lower left. So the dark red colors here indicate places where there used to be permafrost before climate warming, where the permafrost has now been lost. The shaded colors going from yellow up to red, they indicate what we call the active layer depth, or the increase in the active layer depth. The active layer is sort of the surface skin of the permafrost, after the upper part of the soil where plants grow, and that actually, even when there's permafrost, this zone will thaw every summer. It will, when the snow melts, it will start thawing, and there's a dynamic there where part of the soil is seasonally not frozen, and that is how these ecosystems then can sustain life. But you see in this map how this layer has deepened over time, which means that more and more of the permafrost is exposed to decomposition. So looking forward, how much permafrost are we projected to lose? This graph shows how much volume of permafrost will thaw. So it integrates both active layer deepening and the decrease in the permafrost area. So you see there are 3 different warming scenarios here on the bottom axis, 1.5, 2, and 3 degrees global warming, which of course translates to a higher warming in the Arctic, because the Arctic warms faster than the rest of the world. On the left-hand side, you see the scale trillions cubic meters thawed. So these are really large numbers. So by 1.5 degrees, we expect to have thawed a little more than 2 trillion cubic meters. And actually going to 2 degrees, this loss is more than doubled, up to 6 trillion cubic meters. And the 3 degree world, we see a very big loss, exceeding 10 trillion cubic meters. The right-hand side of the graph shows the percent of today's permafrost that is lost, which ranges from 10% at 1.5 degrees up to almost 50% in the high warming scenario. And here I think this is these are alarming losses, potential losses of permafrost. But I think we can also sort of flip this around and think of it of how much permafrost can we actually save if we reduce emissions quickly. And you see here the difference between a 2-degree scenario and a 1.5-degree scenario is really big. And the only way to save permafrost is to reduce anthropogenic emissions. There are no other geoengineering solutions or similar by which the permafrost could be saved. The only way we can keep this ground frozen is by keeping the temperatures down. So then why is it important that permafrost is being lost at ever greater rates? Or in the context of climate, we are really concerned about the permafrost carbon feedback. There are other negative effects of permafrost thaw, including infrastructure damage, loss of traditional livelihoods, ecosystem disturbances, loss of potential biodiversity, and so on in the Arctic. But for climate, the permafrost carbon feedback is the process that we're really concerned about. And what happens is, in a simple way, is that the temperature rises because of global warming. This leads to permafrost thaw and warming. And when the permafrost thaws out, there's a lot of carbon that was frozen that is now being exposed to decomposition by microbes in the soil. And they produce carbon dioxide and methane as part of their respiration, which goes into the atmosphere as greenhouse gases and speeds further warming. So we have a positive feedback loop that makes the warming ever greater. And the reason that we're concerned about gas fluxes from permafrost is because the permafrost contains a very large amount of carbon. This slide here shows bubble plots where the sizes of the bubbles represent size of those pools of carbon in the global carbon cycle. So these are all of the active pools that we turn over at timescales that are relevant to humans. The atmosphere, almost up to 900 gigatons. You can see the pre-industrial atmosphere in shaded gray there, which was around 600 gigatons of carbon. And 1 gigaton of carbon is 1 billion tons of carbon. So it's a very big number. Vegetation, all the living vegetation on Earth contains roughly 500 gigatons of carbon. And the biggest active pool in the global carbon cycle is the soil. Soil, if you go down to 3 meters globally, contains around 2,500 gigatons of carbon. But a very substantial part of this is actually made up of the permafrost. So permafrost soils and deeper deposits contain somewhere between 1,400 and 1,600 gigatons of carbon. So this is 3 times as much as all of Earth's vegetation, or twice as much as is present. And so we have an opportunity here, or there is an opportunity still to limit emissions from permafrost, limit the damage to the permafrost systems. And I have a quote up here from Marcus Aurelius. What we do now echoes in eternity, which is, you might recognize it from the movie Gladiator, but it's also a quote from a Roman thinker. And the point I want to make here is that the response of the permafrost is something that, if we thaw it, we are committing ourselves to a very long time period of increased emissions from the permafrost. Permafrost effects from the permafrost will be felt well beyond year 2100. So even if a lot of scenarios end by the end of the century, the permafrost is not going to end, or the thawing is not going to end by the end of it. Permafrost responds relatively slowly but inevitably to warming. So thaw that we have already initiated will continue for centuries, even if temperatures were stabilized today. It takes a long time for the permafrost to reach equilibrium with climate. And models do project a continued increase in carbon emissions from the permafrost for several centuries beyond the year 2100. So if we start thawing the permafrost now, we are really committing ourselves to the use of negative emissions technologies for several centuries to keep, to compensate. So exactly how much emissions do we predict, or what do the models project, and how fast? This slide shows 3 different warming scenarios and estimated gigatons of CO2 equivalents emitted by the end of the century. So you see At 1.5 degrees, we're looking at something around 100 gigatons of CO2 equivalents. And note that 1 gigaton of carbon equates 3.7 gigatons of CO2. So the units here are different. At 2 degrees, it's quite a bit higher than that, and at 4 degrees, it exceeds 200 gigatons by the end of the century. An important message that we also want to highlight is that overshoot scenarios would add around 50 gigatons of CO2 to the low emission scenario. And overshoot is when we would allow the temperature to actually exceed beyond 1.5, and then using negative emissions, we would pull it back down again. The thing is that during this overshoot warming, the permafrost that thaws at that time would keep emitting carbon, and this would happen. And if we look at even longer time scale of multiple centuries, then these emission numbers roughly double, and especially in the high warming scenario, you see potential high ranges that go very high. So these are significant numbers already, but unfortunately, this is not the full picture. There are a set of processes which we call abrupt thaw processes, or thermokarst, which is the effects of ground ice melting away and the ground collapsing. This is what you see in this photograph that you already saw before. When the ice in the ground starts disappearing, water can penetrate into the soil. Water is really efficient in pulling the heat into the soil, thawing it quickly, and the ground starts to collapse. And this can happen quite rapidly, and it can penetrate very deeply into the soil, and you can get locally you can get quite catastrophic consequences, as you see here in this photograph. Note that there's a person for scale there in the image. You see the scale, the sort of spatial scale of these processes. Unfortunately, these processes are not in the Earth system models that were used to generate these projections. So basically, it remains unaccounted for in the models and in any sort of broad-scale modeling scenarios. So a recent study has done a first estimate of this, which indicates that it can add a lot of carbon. So this schematic here shows you over time how abrupt thaw happens. On the left, you have stable permafrost, and you see, if you look below there, you can see that this is ice-rich permafrost. So this only occurs in places where there's a lot of ice in the ground. And this system is a sink of carbon dioxide and neutral when it comes to methane, basically. Then as warming comes in, permafrost starts to degrade. So going slightly to the right there, we can see loss of ground ice as the active layer becomes deeper, and also the ground starts to slump down when the ice is gone, because the volume that the ice occupied will just drain away. And now this system has shifted to becoming a source of carbon dioxide, because more carbon is available for decomposition. And as time and warming progresses, we can have a full abrupt thaw collapse. All of the ground ice is gone, and we end up with an ecosystem that looks completely different, has gone from stable tundra to a lake, a post-thaw lake or a thermokarst lake. And now we have forced the system into a sink both for carbon dioxide and for methane. So the combined effect of abrupt thaw processes are basically, they double the radiative forcing compared to projected gradual thaw from models. So these are results from a recent study just accepted in Nature Geoscience with the lead author Merit Turetsky from Instar. So this graph summarizes the combined effect of a simplified model that took into account different types of abrupt thaw that we have. And you can see net radiative forcing in the blue from methane and in the red from carbon dioxide, and the black curve indicates a cumulative loss of carbon from the ecosystem. And note that the x-axis is years, so you can actually see that it starts ramping up by 2100, but you do get a strong increase, and it continues to 2300 and beyond. So if we sort of summarize what this means for emission numbers, the previous estimate of the permafrost carbon feedback, these numbers are for RCP 4.5, which is a little more than 2 degrees of global warming. About 1 gigaton of CO2 equivalent released per year now, and at the end of the century expected to go up to about 2 gigatons per year. So this would equate half of all of EU emissions for 1 year or per year. But we need to add the abrupt thaw numbers to this, and we get up to 3 or 4 gigatons per year by the end of the century, which will then which means that by the end of the century, the permafrost will emit about as much greenhouse gases as the EU does today. And on the long term, the emissions are projected to accelerate. So by the end of 2300, we're actually up to twice EU 28 emissions per year. So this is a very significant feedback. And it will be effective for a long time. And of course, this impacts our carbon budget, the remaining carbon budget that we have, that we are able to emit while still staying under these target temperatures. This graph shows the remaining carbon budget in gigatons of CO2 equivalent for 1.5 degrees and for reaching 2 degrees. And the full combined bars are the carbon budget estimates. The pink parts of the bars show how much of that budget is eaten up by permafrost thaw alone. So you see, especially in the low emission scenario, in the low warming scenario, the permafrost consumes more than a third of our remaining emissions budget. So this is something that really needs to be accounted for, and quickly, in the negotiations. And there are numerous and alarming signs that this is happening already. It's not something that we just see in the future. These photographs are from a recent paper, and there are several recent papers demonstrating that massive abrupt thaw is already occurring even in very cold permafrost. This is from the Canadian high Arctic. You see a typical high Arctic tundra in the upper photograph in 2005, and the researchers came back 10 years later, and it looks completely different. The tundra is starting to transform into a different ecosystem. Lakes are forming, and this is really becoming a source of methane and CO2. So what has happened here is that the ground ice has started to disappear, and the whole ground is slumped down, and it's becoming essentially another system. And this is critical because, according to the really good permafrost models, this is not supposed to happen for another 70 years. It's 70 years too early for this permafrost to thaw. And the key here is that these are really abrupt thaw processes or thermocars that are not really represented in the model. So that's why this is happening even quicker than what has been thought. And there's a strong case for limiting warming to 1.5 degrees to really try to keep most of this carbon in the ground. There are also important considerations when it comes to overshoot scenarios. So here, it's written here on the slide, overshoot and ground ice. And the key thing here is that any loss of ground ice is irreversible. So that is the key message. Keep in mind. The graph shows time on the lower axis and temperature on the y-axis. And the black line is representative of a target temperature, hopefully 1.5, if that is where we go. And the green line takes us to the target temperature without any overshoot. And you see a small shaded area above the green line indicating additional feedbacks that are not yet in the negotiations or in the numbers. The red line, on the other hand, follows a so-called overshoot scenario that would allow more warming to occur, and then we would pull the warming back down, or the radiative forcing back down with some negative emission technologies. And this adds even more feedback, so the overshoot would be even bigger because permafrost and other feedbacks would actually increase the overshoot even further than the models would suggest. And importantly, the fate of permafrost or of most cryosphere components under such scenarios is that they will keep going. Abrupt thaw and collapse is in essence non-reversible. So this orange line shows sort of a conceptual idea of what would happen to the permafrost under this scenario, where it follows the upper trajectory of the ocean warming and it does not go back down. Because when the ground ice is gone, it is not going to regrow in a matter of it takes many centuries for the permafrost to go back in millennia. So additional greenhouse gas forcing from abrupt thaw will continue for a very long time. at the level of the overshoot maxima, which is a very something we very much want to avoid. So, concluding remarks, summarizing our findings on permafrost. The permafrost carbon feedback does severely limit the remaining carbon budget, and it needs to be accounted for. Rapid emission reductions saves massive areas of permafrost. We save 2 million square kilometers of permafrost if we go for 1.5 rather than 2 degrees. And unfortunately, accounting for abrupt thaw processes nearly doubles the permafrost carbon feedback relative to earlier models. And the permafrost carbon feedback will respond over many centuries to greenhouse gas emissions made today. And thermokarst so the ground collapse is irreversible at policy time. Global stabilization at 1.5 instead of above 2 could avoid permafrost emissions roughly equivalent to all of EU 28 emissions. So this is very simple. Thank you.
All right, thank you so much, Gustav. Actually, I'll start off with a question. Would you mind explaining maybe just generally the process that converts carbon in the ground to carbon dioxide or methane in the atmosphere?
Yes, sure. So basically, the carbon in the ground is usually some part of the soil. So soil will contain old plant remains and plant residues that stay in the soil over a long time and can accumulate. So these are all parts of roots and leaves and other dead organic material. So this is in the ground, and in a normal soil, so to say, where there's no permafrost, there will always be a turnover of this carbon because microbes, so bacteria and fungi, will be decomposing this carbon. They're basically organisms that live on eating the carbon in the soil, and they respire it. And when they eat this carbon, what they respire, what comes out as the end product, it's carbon dioxide if it happens in an area where in an environment where there's oxygen. And if these bacteria would be eating, or the fungi would be decomposing in an anoxic environment, this mainly is relevant for bacteria, where there's no oxygen, they would produce methane instead. And for the permafrost, the key here is that this soil carbon has been building up for thousands and thousands of years. A lot of the permafrost can be 100,000 years old. So the carbon has been accumulating in the soil for many thousands of years, and the permafrost has been protecting it. There's almost nothing happens in the frozen soil. But when it thaws out, then all of a sudden, this really old carbon that's been lying around frozen for thousands of years is all of a sudden available for microbes to start decomposing it. And then you actually have an unbalance of there's a lot more carbon in the soil all of a sudden, and the ecosystem goes from being a sink of carbon, because otherwise the plants will actually pull carbon out of the atmosphere and it will be a sink. But now we get so much new carbon that is available for decomposition that it turns into a source because the bacteria are eating the soil carbon.
Just to sort of follow up, so the difference between what's emitted is a difference in the bacteria that are operating, right? Is that?
Yes.
Okay.
Exactly. So different bacterial communities are adapted to different conditions. So if you are under a wetland or in a lake that is stagnant, then the oxygen will be depleted quite quickly. And if it doesn't mix, there's not a lot of oxygen coming into the deeper part of the lake. So there you will have bacteria that specialize on decomposition under low or no oxygen conditions. And because they don't have, CO2 is composed of carbon and oxygen. So because they have no oxygen, they can't use CO2, and instead they have a different pathway that produces methane. So it's just different bacterial communities that respond to the conditions that they live in.
Yeah. And could you go back to the slide that showed sort of the committed warming, because I think that was an interesting one in terms of over centuries. Yeah, back another that took things out year-wise.
Oh, this one?
No, further. Or maybe there's a delay on our...
That one?
Yeah, this one. So this is the additional warming, or the additional emissions then that are going to occur. So you need to add the first 1.5 by 2100, and then the second 1.5. Is that scale around 200 years, 300 years? And is it in addition to the 2100?
That as multiple centuries, because the models. So these results are based on sort of several different models, and then making box plots of sort of the. And because the models differ quite a lot in the timing of when this will occur, we have put it down as multiple centuries. But I would say that 2300 can be considered sort of a midpoint of those other numbers. The further you go out into the future, the bigger the uncertainties in the rates at which this will occur are.
Yeah, so these are sort of legacy emissions then that are going to require negative emissions to offset them.
Yes, yeah, exactly. So, I mean, thawing the permafrost and sort of waking this feedback up is something that commits us essentially to employing negative emissions technologies to keep this, or to sort of compensate for this effect over centuries.
Other questions? Doesn't look like there are any other questions. So thank you so much for a really fantastic presentation, and we'll hope to see you later. Thanks so much for all your contributions to this. Yeah.
Thank you. Have a good continuation of the COP. Bye.
Thanks for tuning in. Please join us again in about half an hour at 5 p.m. for our last presentation on Greenland and Antarctic ice sheets and sea level implications. Hello and welcome to the Cryosphere Pavilion. Thanks so much to those of you who are here. I know there's a lot going on, and thanks to those of you tuning in online. My name is Hannah Baranis. I'm a PhD student at the University of Massachusetts in the United States, and I'm standing in for Rob DeCanto, who's a professor at the same institution and was also a lead author on the IPCC special report on the oceans and cryosphere in a changing climate that was released this past September. So there are three main things I want to communicate today. First is just share some of the really, I think, incredible science that has gone into improving our understanding of how ice sheets and sea level are going to respond to climate forcing. And the second is that right now we're already locked into centuries of future sea level rise that are going to be difficult to adapt to. And a lot of the time when you look at projections, you see these really big uncertainty bounds around the central estimate for sea level rise. And I'm hoping that by explaining some of the science, I can communicate that we are not uncertain that that trend is going to continue. What's uncertain is sort of, exactly the timing and the speed of it. And sort of the third piece that's a little bit more good news is that as I explain the science, you're going to see that there's a really incredible role for policy to make a difference in whether we're going to be experiencing sea level rise on the order of centimeters per year that are too fast to adapt to with engineering solutions, or we can sort of continue the slow, gradual rates we're seeing today. All right. Whoop, started at the end instead of the beginning by accident. Okay, so today the International Cryosphere and Climate Initiative released the Cryosphere 1.5-degree report. And I know it's not the most exciting way to start a talk, but I want to start off just by reading some of the key findings of that report that highlight the temperature sensitivity to the ice sheets. So there is strong consensus that the risks of extensive melting from the ice sheets increases as both the peak in global temperatures and the rate of warming rises. Today, so this is going to go through a 1 degree scenario, 1.5, and 2+, so you'll see the role of policy here. Today, if we could hold at 1 degree above pre-industrial temperatures, we are still likely committed to a very slow but unavoidable 1 to 3 meters minimum sea level rise, but over thousands of years. Risks substantially increase at 1.5 degrees, with the possibility of 6 to 9 meters of sea level rise, coming from additional loss of Greenland and Antarctic ice, though this too would likely take many centuries to occur. Then at 2 degrees, there's greater risk of devastating sea level rise because of the West Antarctic ice sheet and Greenland crossing thresholds for near complete melt, with vulnerable points for the much larger East Antarctic ice sheet as well. The duration and extent of warming above 2 degrees will increase the risk, speed, and inevitability of the above changes. However, these processes, even West Antarctic ice sheet collapse, can be slowed, potentially by thousands of years if temperatures remain close to 1.5 degrees, with an aim to return below that level as soon as possible. Okay, so thanks for bearing with me. So current NDCs are completely inadequate to prevent catastrophic melting that's already started in the future. All right, so let's start with what we've observed over the last 100 or so years. The world's tide gauges, which have been measuring water level for about that long, show an increase in sea level of about 15 centimeters over the 20th century. And that's a number to keep in mind as we talk about future projections. And from this curve even, you can see that there's a slight banana shape to it, maybe a little uptick in the last few decades, and we'll zoom in on that, just to the satellite era where we have very precise measurements of the ocean surface. It becomes really clear in the satellite era there's that banana shape to the curve. So the rate of sea level rise is increasing, what we call an acceleration. And so the current rate of sea level rise is about 3.6 millimeters per year as a global average. And this is already double the rate of sea level rise we saw during the 20th century or in the 1900s. So that's that acceleration. And I want to make the point that sea level rise does not impact all people equally. in some places in the Earth, some people have not really felt that 15 centimeters of sea level rise yet. But if you live somewhere like the South Pacific, you're really feeling it. And that just has to do with places where the ocean is heating up the fastest and where winds and currents are piling up that warm water. And then if I could zoom in on the coast, the coastline at different places, you'd also see a lot of variation in rates of sea level rise, because there are places where the Earth is either rising or sinking in response to the Earth adjusting from the load of ice sheets during the last glaciation due to modern day tectonics or due to extraction of groundwater. And this type of variation is going to become really important when I start talking about ice sheet loss. So we'll revisit it. And so just to drive home the point that this 15 centimeters of sea level rise is already really impacting people. So what this figure from the SROC is showing is places where, so taking the flood that on average used to occur once every 100 years, these colors are showing the year when that 100-year flood becomes the annual flood. And it's sort of ironic, the places with the black dots where the 100-year flood is already being experienced annually are at the margins of the figure. So talk to someone who's planning to redo this figure and put the tropical Pacific in the middle. So it doesn't affect everyone equally, and it's already, that 15 centimeters is already really affecting people. Okay, so there's a lot going on in this figure. This is kind of an advertisement for the SROC that just came out, showing all the different components that contribute to sea level rise. And I recommend taking some time to study it later, but for now, there are just a couple things I want to point out. So over the 20th century, or during the 1900s, thermal expansion of ocean water was the dominant mechanism driving sea level rise. So that's just a given mass of water takes up more space when it's warmer. But then moving into the 21st century, a lot of the acceleration in sea level rise has come from the contribution of land-based ice to sea level rise increasing. And so this comes from mountain glaciers. And you might not be able to see this number too well, but the 0.5 meters of sea level equivalent, that's the total amount of potential sea level rise locked in all of the Earth's glaciers, which is significant given the impact that 0.15 meters of sea level rise has already had. But what's sort of really concerning are these beasts in the corner, the Greenland and Antarctic ice sheets, which have 7 meters of potential sea level rise locked in Greenland and 57 meters of potential sea level rise locked in Antarctica. And so what I'm going to go through next, so these two ice sheets are fundamentally different, and each of them have thresholds that at different points will lead to irreversible melting of those ice sheets, irreversible and accelerating melting of those ice sheets. And I mentioned before that once we start thinking about ice sheet melt, sort of the uneven distribution of sea level rise becomes extra important. So before we dive into this figure, what's going on here, ice sheets have gravity. They're so massive that they actually pull the surface of the ocean up towards them. So when they lose mass, sea level drops near the ice sheets, sloshes away from them, and rises unevenly. That water gets distributed unevenly in other parts of the globe. So that's one thing that's happening. Second, because the ice sheets are so massive, as they melt, you're significantly redistributing the Earth's mass, and that changes our pole of rotation. And so people have modeled that distribution, that uneven distribution of sea level rise from each of the ice sheets melting. So the left-hand figure is showing what happens when Greenland melts. The right-hand figure is showing what happens when Antarctica melts. The scale on the right is a fractional scale, so I think the easiest way to think about it is if you follow the transition or the interface between the yellow color and the orange color. That's where you get the relationship you expect. So 1 meter of equivalent sea level melting from Greenland, 1 meter of sea level rise. Everywhere it's blue, you get less. Everywhere it's red, you get more. And so a couple things to point out. The figure on the right has often been called the karma figure for North America. For 1 meter equivalent of melt in West Antarctica, we experience about 130% of that amount of sea level rise in North America. And then another thing to point out, there's sort of a lot of question as to, which ice sheet is going to contribute when. And in either scenario, the tropical Pacific is kind of sitting like in a bullseye for experiencing more than the global average of sea level rise. All right, so right now, Greenland is losing ice at about twice the pace of Antarctica, but Antarctica could soon take over. And maybe just focus on the left-hand figure. Those are changes in mass of the ice sheets measured by satellites. And so let's start by talking about some of the instabilities and positive or thresholds we can cross with melting in Greenland. So there are two primary feedbacks that can cause rapid melting in Greenland. One is the melt albedo feedback. So as ice melts, it forms water on the surface of the ice sheet, which is darker in color than ice. And as the ice sheet gets darker, it absorbs more sunlight and warms things further. The second, the height melt feedback, this is kind of the more significant one. So right now, the surface of the Greenland ice sheet in the center is sitting at about 3 kilometers above sea level. And as we all know, just from living on the planet, as you go down in altitude, it gets warmer in a given location. And so as we melt the ice sheet and the surface drops, it enters warmer and warmer temperatures. And that's a process that is not reversible on human timescales. So once we start dropping down, we're committed. And so then the question is, at what temperature and at what rate does this happen? So these are just model simulations of the Greenland ice sheet. So the modeler here just warms the atmosphere to 2 degrees, 4 degrees, 6 degrees above current temperatures, and then lets the Greenland ice sheet change. And so in that figure on the left, on the vertical axis, that's showing ice volume, so starting at 100%, and then after you warm things up, you see volume decreasing. And on the x-axis is time in thousands of years. And I think what's really striking in that figure is the big step function increase between 2 degrees of warming and 4 degrees of warming. And again, that's that difference between slow, gradual sea level rise we can adapt to versus rapid sea level rise that we can't adapt to. And so a last really important thing to point out here, that those temperatures, do not think of those as the global average. The Arctic, and so the region that Greenland is in, is warming at twice the pace of the global average. So its sensitivity is quite a lot higher. Okay, so Antarctica is a different beast. And so the person I'm standing in for, Dr. Rob DeCanto, what he's been really sort of instrumental in doing is taking observations of how Antarctica behaved in the past when conditions were warmer, and trying to incorporate new physics into models of the ice sheet that can reproduce past conditions reliably so that then we can trust them when we run them into the future. So a little more detail on that. We're currently in a warm interglacial period. About 20,000 years ago, there were glaciers covering a lot of the northern hemisphere. That was the last glacial period. And then before that, there was another interglacial period where temperatures were roughly similar today, and sea levels were 8 meters higher than they are right now. And carbon dioxide was lower. And so Andrea Dutton from the University of Florida has gone all over the world mapping old ocean shorelines. So in that left-hand image, she's standing on an old coral reef that's sitting 8 meters above sea level that she can date to the last interglacial period. And there's geologic evidence from all over the world like that. So when I mentioned in the last interglacial, temperatures were similar, but carbon dioxide was lower. To find concentrations of carbon dioxide in the atmosphere that are similar to today, you have to go back 3 million years to a time period called the Pliocene, when the atmospheric concentration of carbon dioxide was between 350 and 410 parts per million, and sea level was 6 to 30 meters higher than it is today. There's a bunch of new studies coming out that are really sort of narrowing that range into the 20 to 30 meter range. And so then the challenge is to develop ice sheet models that when you run them with similar climate conditions to these past periods, can you reproduce the amount of sea level rise observed in the geologic record? Okay, and so I mentioned Greenland and Antarctica are fundamentally different, and the fundamental differences between those two has been key to incorporating physical processes into ice sheet models that can reliably reproduce past conditions. So Greenland is on the top, Antarctica is on the bottom. What those left-hand maps are showing are the elevation of the bedrock that each ice sheet sits on. So at the margins of Greenland, most of the ice sheet is above sea level, whereas in Antarctica, there are portions of the ice sheet that are grounded on bedrock 2 kilometers below sea level. And significant parts of the ice sheet's margin are in direct contact with the ocean. Okay, so that's one important thing to remember. A second important thing is that the land is a little bit higher at the margins of Antarctica, and they slope inwards towards the middle of the ice sheet, particularly in West Antarctica. So I'm going to call that a reverse sloping bed. So sloping from higher at the margins to lower down in the middle. And I'll explain why that is important. Okay, so the new physics incorporated into these models that accelerate ice sheet breakup are sort of a 3-step process. So starting sort of from farthest out at the margins and then moving into the interior of the ice sheet as things melt. So at the edges of Antarctica, a lot of the ice actually is not grounded, it's floating. So where the ice leaves bedrock, we call that the grounding line or the grounding zone, and then it pinches out into these ice shelves that are actually quite thick, like a kilometer thick sometimes, that are floating. So when these melt, they're already floating, so they don't contribute to sea level rise. But losing them has really important implications for the ice behind them. And they're particularly vulnerable because they can be melted from above by warm air temperatures and below by warm ocean water. And so you see on the top left, there are observations that the Southern Ocean around Antarctica is warming. Then on the right, those red dots are showing areas where ice shelves are breaking up and melting. And this was actually observed in the early 2000s on the Larsen B ice shelf in West Antarctica. So these sorts of those dark areas on the surface of the ice shelf in the image, those are meltwater pools sitting on the surface of the ice shelf. And then as soon as those appeared, pretty rapidly, just a few months later, the ice sheet collapsed. So again, this in itself does not contribute to sea level rise, but what happened is the ice behind the ice shelf sped up in terms of its motion into the ocean by a factor of 8. And you can the reason that is, you can kind of think of it with a building analogy. So the ice shelf actually buttresses the ice sheet behind it. So as ice advances, that ice shelf can there's friction on the sides of it, and it can catch on features on the ocean floor, and it can hold back flow of ice from the land behind it. Okay, so that's the first thing that can happen is ice shelf breakup. Okay, so the next process is something called the marine ice sheet instability. Once you melt away the ice shelf and you start speeding up ice from inland, you are exposing the ice sheet to the possibility of retreating where it's grounded. And this is now ice that contributes to sea level rise. And so two really important things. Remember, we're on a reverse sloping bed. So as the ice sheet retreats, the thickness of the ice above the grounding line, or the new grounding line, gets thicker and thicker and thicker because of that reverse sloping bed. The second really important thing is this number 5. So the relationship between the thickness of the ice above the grounding line, which is getting thicker and thicker, and the speed at which the grounded ice flows into the ocean, contributing to sea level rise, is raised to the power of 5. So once it starts, it accelerates. And this is what's called the marine ice sheet instability, and caused by the reverse sloping bed in Antarctica, and particularly in West Antarctica. And back when the Larsen B ice shelf collapsed, we actually got our first observation of a marine ice sheet instability. So the ice sheet collapsed, and then those lines are showing how rapidly one of the tributary glaciers started surging into the ocean. Okay, so the third process is called the marine ice cliff instability. And you can see from that image, where the new front of the ice is, there's a cliff. Here's a closer up image of what these things look like. So once you have glacial ice, not ice shelves, flowing into the ocean, they end in a cliff. And ice has a finite material strength. So if you expose these big cliffs, these can be, usually once they become like around 100 meters high, the stress on the ice cliff exceeds the material strength of the ice, and it can catastrophically fail. And here's a video sort of showing you the scale of this kind of process. I guess this is the moment it stops working. Okay. All right. Sorry about that. So again, there's these three processes that lead to instability in Antarctica. The first is breakup of ice shelves. Second is the marine ice sheet instability. And the third is the marine ice cliff instability. All right, so I mentioned that a lot of Rob's work has been trying to incorporate these processes into ice sheet models, and then first trying to run them back in time to see if we can match past conditions during the last interglacial and then during the Pliocene 3 million years ago, sort of just to see if they can accurately reproduce past conditions so we can rely on them for future projections. And just sort of to show you what a big impact these two processes have. Forcing the model with last interglacial conditions. When Rob adds in the marine ice sheet instability as a process in these ice sheet models, he gets an additional 1.7 meters of sea level rise just from Antarctica. That's that middle figure. And then when he adds the marine ice sheet and marine ice cliff instability, that number jumps up to 4 meters of sea level rise. This is just the same figure showing the model run under Pliocene climate conditions when CO2 was at around 400 parts per million. So there's 3 meters of sea level rise with just the marine ice sheet instability, and then close to 20 meters of sea level rise for the marine ice sheet and marine ice cliff instability. Okay, so now running these models into the future. Again, the take-home message here is that current NDCs are not enough to prevent these processes from happening catastrophically fast. So the bottom figure is showing just projections out to 2100, and this is just the Antarctic contribution to sea level rise. These are scary numbers when you think about the fact that 15 centimeters of sea level rise has occurred over the last 100 years, and that's already having devastating impacts for people, particularly living in the tropical Pacific. Yeah, and so then a second thing to highlight here is sort of the inadequacy of only taking a view of sea level rise out to 2100. So if you jump up to the top figure, you can see that those, let me back up for a second. So the three different curves are showing the same ice sheet model run for 3 different emission scenarios. RCP 2.6 is a really dramatic cut in emissions scenario, and RCP 8.5 is a scenario where we sort of continue on the trajectory of increasing emissions and business as usual. And so where you really see very strong divergence in those trajectories is beyond 2100. That's the pessimistic view. The optimistic view is that difference is the role of policy. Again, we're committed to sea level rise in the long term from ice sheets. But rate of sea level rise is incredibly important when you start to think about adaptation. And just for those of you who are curious to dig into the numbers, something to note is that even though Rob DeCanto was a lead author on the SROC, this exact study was not incorporated into the SROC because they think the increase in temperature that he ran the models with above Antarctica was just a little bit too fast. But nonetheless, the scientists working on the SROC pushed hard to get a long-term view of sea level rise beyond 2100 to show the really, really strong impact that policy can have on future sea level rise. And still, the sort of just the middle of the high emission scenario is 84 centimeters of sea level rise. And just one last thing to point out, that as the more we understand about ice sheets, the worse the projections get. So on maybe just focusing on the RCP 8.5 scenario on the right, the high emission scenario, this is the first, the gray is showing the AR5 IPCC report sea level rise projections compared to the ones in the SROC that just came out this past September. And it's the first time that sort of the likely range in sea level rise went upwards of 1 meter for 2100. Okay, so I will stop there, and if you have any questions, I'd be glad to take them.
Thank you for the presentation. I guess what's the difference between an ice shelf and ice sheet? Is there like a thickness difference, or there's like anything quantitatively makes them a shelf versus a sheet?
Yeah, great question. So a shelf is just floating ice. That's normally found at the edges of ice sheets. And ice sheets are big masses of ice that are usually highest in the middle, and then they flow outwards under their own weight. So the only ice sheets on Earth are the ones on Greenland, and then the two on Antarctica. So there's one on the West Antarctic continent and one in the East Antarctic continent.
So the sheets are not attached to a rock or any ice underneath, if I'm hearing you correctly. Is that right? It's kind of free-flowing?
Other way around. So
okay.
Ice sheets are grounded on bedrock. Yep, and
yes,
ice shelves, yeah, exactly. They're not attached.
Gotcha. It's not defined by the thickness and how large and how tall that particular shelf is, right?
No.
It's just the attachment. Okay, thank you.
But ice sheets are much thicker than ice shelves, yeah, because they're these continent-scale ice masses.
Thank you.
Mm-hmm.
Any other questions? Okay, well, thank you very much. We're going to have one more presentation at the end of the day today that summarizes the Cryosphere 1.5 report. But thank you, Hannah, for the last scientific presentation of the day and in the Cryosphere Pavilion.
All right,
So,
thank you.
Thanks so much.
Good evening, everyone, and welcome back to the Cryosphere Pavilion. We are actually at the very last presentation of our nearly 2 weeks here at COP25. And today we have been going through the findings of the Cryosphere 1.5 report that was released today here in Madrid in virtual version. We will be coming out with the print version in January. Probably in connection actually with the meetings in Davos, going from the climate community here to the business and decision maker community that one tends to see there, because these are important messages as countries now leave COP25 and over the next 3 to 9 months begin coming up with their NDCs for 2020 that in most cases will cover the period through 2030, which is that time period that the special report on 1.5 degrees identified as kind of our last best chance to stay under 1.5 degrees. And the consensus view of the Cryosphere 1.5 report, which had over 40 cryosphere scientists as authors and reviewers, is that 1.5 is a true outer guardrail for the cryosphere and for the feedbacks that could otherwise change the entire climate system of the Earth into a very new state that we haven't seen for several million years at a minimum, maybe as much as 60 million years. So it would be a very different planet if we allow especially 2 degrees to be breached. I'm going to be going through some of the major findings of this report, which was aimed at combining the special report on 1.5 degrees that came out in October 2018 and the special report on oceans and cryosphere that came out this past September, as well as updating with some of the science that has come out since. One of the really striking things about cryosphere science these days is how very quickly it's evolving. And so even since the SROC, as it's called, closed its literature, there have been a number of findings, especially when it comes to permafrost and Arctic sea ice, and the science is moving very, very quickly, and these reports can only barely keep up. These are the thresholds that we discuss, and these are the ones that have really special significance when it comes to the gradient that we're in right now between about 1 degree today all the way through 2 degrees in particular and above to 3 and 4 degrees. Permafrost thaw has been ongoing for quite some time and will continue to happen at ever higher rates the higher temperature moves. The West Antarctic ice sheet probably tipped into a state of complete collapse that became inevitable sometime before 2015 around 0.8 degrees. I'll talk a bit more about that later. Mountain glaciers are undergoing very extensive loss, even today at 1 degree, and that will continue again as temperatures rise. Arctic sea ice, of course, has been declining in terms of both volume and extent or area. It is about only 25% of what it was at the middle of the last century, and it is projected to continue decreasing until there is no summer sea ice for a period each summer. The ice sheets of Greenland and Antarctica are beginning to react, and polar ocean acidification is already showing some signs in polar oceans. These colder waters are undergoing acidification much more quickly than the warmer waters, and we're beginning to see shell damage even today. So beginning with the glaciers, at 1 degree C, nearly all of these will be lost. In other words, if we were able to hold temperatures today, we would still lose almost all tropical glaciers, those around the equator, in the northern Andes, East Africa, and there are actually some in Indonesia, Papua New Guinea, other than those that are really, really high altitude, such as over 6,000 meters. So those can no longer be saved already at today's temperature. With the mid-latitude glaciers, the picture changes a bit, though. And as you see in the southern Andes, which includes Patagonia, the Rockies in the US, Scandinavia, New Zealand, and especially the Alps of Central Europe and the Caucasus, you really see a big difference between a 1.5 degree guardrail, which is the blue line in these graphs, representing RCP 2.6, and higher temperature levels. And as you see here in the Alps, we we even start to see a bit of regrowth moving towards 2300 in these glaciers. That's because this line is going down. That means, in other words, that you're no longer losing mass, you're gaining mass. And this is the good news, that we actually can determine, if we decide to stay within 1.5 degrees, not to lose these mid-latitude glaciers in the same way that we're already going to lose the tropical glaciers. And then in what are called the high latitude and altitude glaciers, in other words, the polar glaciers around Antarctica and Greenland, and the glaciers of the Himalayas, at 1.5 degrees, we will still lose about a third of these glaciers, but at 2 degrees, that goes up to 50%, and if we hit 4 degrees by the end of this century, we're going to lose 2/3 of those glaciers, and they're enormously important. There was a study that came out just a couple of days ago showing that 2.2 billion people are reliant on the water from these glaciers. One of the most important river basins in the world, in western China, the Tarim, is actually almost exclusively dependent on glacier and snow runoff. It runs off, in essence, into a desert. All of the agriculture there, it's one of the biggest cotton baskets in the world, is dependent on irrigation from the Tarim River. And so these are extremely significant river basins in many cases. In the polar oceans, acidification is a process that is one of the most long-lived. It's the hidden face of CO2 emissions, and the increased acidity takes anywhere from 50 to 70,000 years to come back down to today's levels. The cold waters absorb CO2 much more quickly, and so they're acidifying much more quickly also. But even in the lower globe, if at 1.5 degrees, there are some regions in the Arctic that are going to be corrosive to shell building. Again, even at 1.5 degrees and those CO2 levels. If we reach 4 degrees and the commensurate CO2 levels by the end of this century, then the large portions of the Arctic Ocean and the surrounding northern seas, actually, such as the Bering and the Barents, are also going to be corrosive to shell building. But the Southern Ocean gets engaged as well, and at relatively high latitudes. You can even see that it's touching the tip of South America, Chile, and Antarctica. These are enormously important fisheries, but the species that live in these polar regions are going to be squeezed not only by increasing levels of acidification, but warming waters and also freshening waters as both ice sheets begin to melt. Permafrost, we're looking at primarily in terms of carbon budgets. There's also infrastructure damage, but the real message of permafrost is that the higher temperatures rise, the more CO2 and in some instances methane emissions come from permafrost. It needs to be thought of increasingly almost as another country, another NDC, a naturally determined contribution, although it's not natural because it's responding to human-induced warming. And even today at 1 degree, there's been quite a lot of permafrost lost, but one of the messages of this report is that we also have abrupt thaw processes. This is new science, not included in the special report on oceans and cryosphere. And these abrupt thaw processes are coming especially through heat waves in these regions where you get sudden collapse and erosion of hillsides or the formation of lakes. So permafrost that no one thought would be susceptible to thaw, because it was deeper, is now thawing and releasing its stored carbon. And that carbon, especially when it forms under the lakes under wet conditions, more of that carbon is released as methane rather than CO2. And methane in the near term warms the climate much more quickly, and so you get a cascading series of events from that additional methane that is then going to enhance warming, and you're going to get more and more permafrost thaw as well as feedback such as ice sheet loss. And so this is a really important process, and the estimates right now is that it's going to double the amount of warming coming from permafrost. The other issue with permafrost that is not paid attention to but needs to be done in these climate talks is that permafrost, once it thaws, continues to emit carbon over a 200 to 300 year period. And so even if we're able to bring emissions completely down to zero and become carbon neutral in terms of human emissions, we're going to have negative emissions to offset what is coming from permafrost 200 or 300 years from now. And so that again is an intergenerational legacy issue because we're basically committing future generations to negative emissions just to offset permafrost alone. Sea ice is one of the best known indicators in the climate system of global warming. It tracks fairly closely with CO2 emissions. But one of the, again, newer findings is that the models that have been used to estimate sea ice loss have mostly focused on global models that have always lagged way behind what we're actually observing in the Arctic in terms of Arctic summer sea ice loss. And if you start to calibrate those models with observations, what scientists are finding is that around 1.5 degrees, you may have the occasional ice-free a few days conditions, maybe even sometime in the next 10 years. But at around 1.7 degrees is when you're going to get some ice-free periods every summer. And by 2 degrees, that ice-free period is going to last for several months out of the year, perhaps from July to October most years. And the immediate response might be that's good news for shipping, but the reality is it's really bad news for the global climate because you have this dark ocean water that's able to absorb more heat, and you get all of the feedbacks again from that. More ice sheet melt from Greenland, more permafrost thaw. And so having that ice-free period is really bad news for the climate. And the only way, again, to constrain that is to have lower temperatures in the Arctic, which means lowering of CO2 emissions. But the story of sea ice is not just the coverage, it's also the thickness for the environment. And multi-year sea ice, which you see here in this animation beginning at around the mid-1980s, has been going down. And if you look at the graph in the upper left of this figure, you can watch that going down over the years. It waxes and wanes in the winter and summer, but it has decreased from about a third of all of the ice every year. And it's down now, as you'll see, almost to zero. In 2007, it dropped quite a bit. In 2012, right now, there was another extreme loss. And coming into 2019 this year, the amount is essentially zero. And so we've really eliminated this multi-year ice. And it's really important to the Arctic ecosystem. A lot of attention has gone to coral reefs and their importance as an ecosystem. But actually, this multi-year thick sea ice is its own ecosystem. It's the polar equivalent of a coral reef. And all of the species that live in the Arctic are dependent on that being there. As you can see from this picture, it's a really rich, vibrant ecosystem. It is anything but dead. And the loss of this multi-year sea ice could mean the entire collapse, really, of polar ecosystems and species, and again, the very rich fisheries that depend on it. And finally, moving to this fifth cryosphere dynamic in terms of the ice sheets. What happens at the poles does not stay in the poles. And even under low emission scenarios, by 2050, this is the amount of annual floods. What were 100-year events that are going to be occurring just southeast of Beijing. This is to the new modern super city, Tianjin. And this is the kind of flooding they're going to see on an annual basis, even in 2050. And this is the equivalent in Bangladesh and in the Kolkata region of India. Again, these are due simply to a reevaluation of satellite data. And because of this, we're realizing that even at 1 degree of warming, we're really going to see a lot of flooding on an annual basis now. I spoke earlier about the West Antarctic ice sheet, and the collapse may have become inevitable. I think there's growing consensus that the West Antarctic ice sheet has tipped, and it's going to inevitably collapse, which is going to lead to around 3 to 4 meters minimum of sea level rise on its own. However, if we can stay within 1.5 degrees, that collapse is going to occur much more slowly on a time scale of many hundreds, maybe even thousands of years. years, so at a rate that we're able to adapt to. But if we go higher in temperatures, then that collapse is going to occur much more quickly, possibly as quickly as just a few centuries. So that's a lot of sea level rise to deal with, and keep in mind that in addition to these 3 to 4 meters, you're going to have Greenland and the glaciers also contributing to sea level rise. And we do know that from Earth's past, at the end of the last ice age, sea levels rose between 12 and 14 meters in the space of a little over 300 years. So rapid sea level rise has occurred in the past and may again occur in the future, especially as we hit higher and higher temperatures. And this shows this graphically. This is work done by Andrea Dutton, who actually just got a MacArthur Genius Award. And at 1 degree C, during the last interglacial, we were at 6 to 9 meters of sea level rise. Now that occurred slowly, but that more or less is what we would be looking at 1 degree C. And as we go to more like 1.5 degrees C, that amount in the past in the Earth was 6 to 13 meters, again, taking long periods of time. But as you move from 2 to 3 degrees C, then we're looking at much larger amounts of sea level rise in Earth's past. 3 million years ago in the Pliocene, that's the last time temperatures were at this 2 to 3 degree level. And Andrea has actually updated her figures now for more sites at different points on the planet. And probably that extreme now is probably around 25 meters of sea level rise at the height of the Pliocene, sometime between 2 and 3 degrees. We don't know how quickly this can occur, but the point of this is that I think a lot of policymakers focus on, say, 1.5 or 2 degrees C as new okay mean stable temperatures for the planet. And what the cryosphere researchers, especially the paleoclimatic researchers who deal with ice sheets and sea level rise, are trying to get across is that at 2 degrees, we would have, if we stayed there for a long period of time, a lot more sea level rise. If we exceed that even further, it could occur more quickly. And even 1.5 degrees, which, 6 to 13 meters, that's a lot of sea level rise. So in a sense, if you're looking at long-term temperatures and where we want the climate to stabilize, 1 degree is really the new 1.5 degrees. 1.5 is an outer guardrail. We need to try and get down to 1 degree as soon as possible to prevent these feedbacks from kicking in on an irreversible basis. But again, the hope is that this is sort of in our hands. This final slide looks at future sea level rise scenarios, calibrating them with this paleo observational data. And at RCP 2.6 in this picture, the upper one is what you've seen mostly, which only goes up to 2100. But if you go out to 2500, the cryosphere responds, the ice sheets respond really slowly, but once they respond, they keep on going. And so at RCP 2.6, about 1.5 degrees, a very, very slow rise in sea level shown in that black line at the bottom. As you move up, though, to high emissions, you're looking at, by 2500, as much as 15, 17 meters of sea level rise by 2500. But there's a real role for policy there. And we can constrain this sea level if we stay within this guardrail of 1.5 degrees. So that, I would say, is the main message of all of these dynamics. There's more detail in the Cryosphere 1.5 report, but it's seen very much as a policymaker summary of the SR 1.5, the SROC, and then some of the science SIDS. So you can find it online. And I'm happy to take any questions. Otherwise, I would thank you very much for your attention today, especially for those of you who are watching online. And for the Cryosphere Pavilion, we thank you very much for these 2 weeks. All of the presentations are available online, so you can rewatch or watch some of the ones you might have missed. We'll try and break them up into individual ones as time goes on. But we're looking ahead to moving this science out into the policymaker world over the next year as much as possible. And we hope to see some of you at least at COP26 in Glasgow. So thank you very much. very much love our live streaming crew over the past couple of weeks. Thank you so much, Rodrigo. It really has been fantastic. So thanks so much. And goodbye to everyone online.